Right now. But okay, the option is pretty easy to find. Just under properties, you get it under physical. And another way we can find the center of mass is under inspect. Scroll down to center of mass, and you can just select a specific body or a combination of bodies. And you can see here a simple dot. So that's the center of mass of this link. Now, if I make any changes to this link, the center of mass also changes accordingly. So this is all about CAD modeling and the important things you have to keep in mind. Now let's get back. We've covered so far. We have a robot definition. What defines a robot? The loop, the sense, process, act loop, the key vocabulary, joints, links, end effector, and degrees of freedom. Why we need to assign joint limits on CAD, and how we find inertial properties. Any questions so far? You can raise your hands. Okay, now here's our actual rover for today. It has a 3 degree of freedom planar arm. So it has 3 links, 3 revolute joints, and 1 end effector. And it has a camera. Now the camera is not sitting at the arm's base. It is mounted 5 centimeters to the left and 10 centimeters above the arm's base. We will look at why that information is important in a while. Now let's move on to the next topic, coordinate frames. This is the math of position and orientation. And here's a question. In this image, this point X is the end effector. Now, if I ask you where is the end effector, what would be your answer? Well, if you're giving an answer, you're wrong. It should actually depend on who's asking. Should have specified relative to what. So relative to the room, the answer would be 25.5 and 10.5. But relative to the base, it changes because the base is offset from the global origin. And relative to the joint, again, you get a different value. But see, the end effector is the position is still the same physical point in space, but you use 3 completely different coordinates. Now, all of them are correct, you're just using different reference numbers. So, let's define a coordinate frame. It's defined by majorly 2 things, the origin and basis vectors. The origin is a specific point in space that we call 0, 0, 0, and basis vectors are your 3 orthogonal vectors, the x-axis, y-axis, and z-axis to define direction. And then we have an important convention, the right hand rule. So point your index finger in the x direction and point your middle finger in the y direction. So your thumb would automatically point to you in the z direction. We also have a color convention. X is always red, Y is green, and Z is blue. And this coordinate convention is what every robotic framework, ROS, URDF, RViz, everything you will use further on follows this convention. And why does this matter? What if I mess it up? Well, if you accidentally flip an axis, your robot will move backwards when you give a forward command, and all your sensor data will be inverted. Now let's look at the frames on our 3 degree of freedom bot. We have 4. The world frame. This is fixed to the environment and its origin is at the bot's starting position. It's like the GPS. It's the universal reference that never changes. Then we have a base frame. This is fixed to the robot's base. So if the rover dies somewhere, the frame moves along with it. So it's basically fixed relative to the rover but moves relative to the world frame. And then we have a joint frame. You get 1 per each joint. And this moves along with the joint. Its origin is at the center of rotation of the joint. And then we have the end effector frame. This is attached to the tip of the arm. This is basically the goal. We want to know where this is in world coordinates and we want to control it precisely. So the hierarchy goes world frame, then base, then joint, then end frame. And each frame is described relative to its parent. So when we chain them all together, we get the position of our end effector in world space. Let's look at, I'll explain joint frames better on the CAD model so that we can understand why they move why they move along with the joint. So here I've marked an additional axis. So on each joint, you can see the 3 lines, red, green, and blue. So now when I move this joint, you'll see that the axis moves along with them. And so do all the subsequent ones. Now say this, the joint 2 axis has also moved. And now when I move the joint 2, you'll see that the axis of joint 3 also moves along with it. So it's a downward chain. Everything below it in that downward hierarchy moves along with it. And now when I move joint 3, only joint three's frame rotates along with it. Okay, now that we've looked at frames on an arm, you get 2 extra frames whenever you're working with a mobile robot, one that moves. And those are ODOM and MAP. Now, ODOM is the robot's self-estimated position based on its wheel encoder data. So what it does is every time its wheel rotates, it calculates how far it has moved and updates its estimated position from where it started. So the critical property is that it's smooth and continuous. So every tiny update is a tiny change. Every update is a tiny change. And controllers and planners rely on this smoothness for stable motion. But the critical flaw is that it drifts. Why? Because wheel slips and encoders aren't perfect. So every tiny calculation will have a tiny error. Now that seems tiny, but it gets accumulated. Say after 100 meters, the error is significant. And to fix this problem, map frames comes into the picture. But this is fixed to the real environment, the actual room, the building, or the outdoor space. It doesn't drift, it doesn't move. And what the robot does is that it knows where it is in the map frame through SLAM, which is simultaneous localization and mapping. As it drives, its LiDAR scans walls and features and builds a map. So when it recognizes a specific feature which it has seen before, it goes, oh wait, I remember. And then it corrects its position estimate. So this correction updates the transform between the map and the ODOM frame. A critical property of the map frame is that it takes jumps, so which is why algorithms can't use it. Let's think of an analogy. Imagine you're walking blindfolded through a building, counting your steps and tracking your turns. So your internal estimate of where you are is ODOM, accurate to where you started, but it drifts as errors accumulate. But every time someone lifts your blindfold for a second and you see a landmark, you're like, oh wait, I'm at the stairwell. So you correct your mental position. Now this is exactly what SLAM does. It updates the map to ODOM transform. Now, Now let's state our mission problem precisely. The camera saw the pixel at 320, 180, but these are in pixels, they're not in meters. And the camera has its own frame. So what do we need to do? We need to convert those pixel coordinates to real world metric space. Now this uses camera vision and calibration, which is a whole another topic. So now let's assume that we've got the coordinates in the camera frame. And we know the offset. We know the offset of camera relative to the arm base. So now we need to figure out a way to tell the arm how to move that. Now, but the conversion between the camera frame and the arm base frame is what transformations solve. And that's our next part, transformations. So this just mimics whatever I've said. You have your coordinates in the camera frame and you want them in the base frame. So you need to apply some sort of transformation. Now, transformation has two parts, translation and rotation. Translation is just shifting the origin. I'm saying that my frame is 3 meters to the right of yours. So that's translation. You use a simple vector offset. And rotation is changing the axis direction. My frame is tilted 30 degrees relative to yours. Now that's a rotation, and that's where the math gets complicated. But here's a really important insight. You can always get from one frame to another using some combination of translation and rotation. And another important thing is if I know the transform from A to B and the transform from B to C, I can just combine those two by multiplying them together and get the transform from A to C. So you can chain transforms. Now translation is pretty easy. Say we've got the coordinates of the sample in the camera frame, that's X cam and Y cam. I just add the offset, like I've said, 5 centimeters to the left and 10 centimeters above, and I get my target position. Say it's 20, 20 centimeter. So that seems pretty simple, right? Because it's translation. Let me show you a simulation kind of thing. So this is 2D transforms. Do not pay attention to the homogeneous matrix right now. Look in the box under it. So this point P is fixed relative to the robot frame, and when the robot moves, the coordinates of P with respect to the world frame would change. So pay attention to the world frame coordinates, which are written in purple. So now as I move the robot, you can see now how the y coordinates are changing, and now the x coordinates change. So this is just simple translation transform in 2D. The same in 3D. Again, look at the world frame coordinates. Now as I'm moving along y, you can see that the y-axis coordinates changed, and now the z-axis, and now the x-axis. So it's just simple translation. You just add the vector offset and you will get your points. Now let's get back to rotation. That is where all the math gets complicated. But before we get into rotation, let's look at what we've covered so far. Robot definition, the loop, sense, process, and act, the vocabulary, why joint limits are important, and how do we get inertial properties. Then we looked at coordinate frames. Why does the concept even exist? And how do I move from one frame to another? That's transformation, and we've looked at the translation part of it. Any questions so far? Okay, then let's talk about rotation now. Now, rotation matrix mathematically describes how one frame is rotated relative to another. There are three basic ones. You must all be familiar with this from math. So Rx theta, Ry theta, and Rz theta, respectively rotated about the x, y, and z axis. Now, a beautiful property about these rotational matrices is that first they're orthogonal. So R inverse is equal to R transpose, and this just makes the computations much more efficient. Now, another way we describe rotations is through Euler angles. Now, these are very human friendly a way to describe rotations. We use three angles. Roll, which is denoted by phi, and this is the rotation about the x-axis. Then we have yaw, psi, rotation about the y-axis, and theta, pitch, which is rotation about the z-axis. Also pay attention to the color convention. X is red, Y is green, and Z is blue. And these are very intuitive. If I say that the camera is pitched down 30 degrees, you immediately know that I mean a rotation about z-axis. But there is one last nasty problem. That's gimbal lock. Now this is one of the most famous problems in aerospace and robotics history. What happens is that when one of the Euler angles reaches 90 degree, no matter what other rotation you do, you just lose 1 degree of freedom. Now as you can see, the jet doesn't really move. So when two of these axes becomes aligned, the math break down and you can no longer represent certain orientations. So you just lose one whole degree of freedom. So this is why robotics uses quaternions. Now Euler angles are easy to understand, but they hit gimbal lock. But quaternions, these are hyper complex 4D vectors. They sound terrifying, right? But they are mathematically perfect. They give you flawless rotations, but they're very hard to visualize and understand. So this is what a quaternion looks like. Q is equal to Q naught plus Q1 I plus Q2 J plus Q3K. Now I, J, K here are all complex numbers, and you have four numbers to describe rotations about three axes. So the extra number is what buys you immunity from gimbal lock. You don't need to understand or derive them today, just know that they exist for a very good reason. And ROS and URDF and every other simulation software uses quaternions for orientation. So whenever you see four numbers describing a rotation, just know that that's a quaternion. Now libraries like NumPy or SkyPy handle the math. So for now, our job is just to understand why they're there. Okay. And then we have another tool, the homogeneous matrix. This is a 4 by 4 matrix that packs rotation and translation into a single mathematical object. So we have R, the top left block, which is the rotation submatrix. This is Rx into Ry into Rz, all your theta rotations. And then we have a translation submatrix. This is P. This is what's your translation vector. And then we the bottom row 0 comma 0 comma 1 is what makes this entire matrix homogeneous. And why do we do this? Because then we can chain matrices with simple multiplication. Frame, you say I know the transform matrix from A to B and then B to C. I multiply these two and I get A to C in one shot. Now that we've covered transformation matrix, we can understand this. So in a 2D transform, you have the first 2 by 2 matrix block is your rotation matrix, and the ones in yellow are your translation vector. So now when I rotate, you see that those values change, and so do the frame, the coordinates of point P in the frame A. Notice how they change now. Okay, and then similarly in 3D, you can rotate about all the three axes. This is rotation about X. You see how the values are changing? And then we have rotation about Y and rotation about Z. So what this is internally doing is just multiplying the transformation matrix to the coordinates to get your coordinates in frame B. And you can see how the Euler angles are changing while I rotate it. Euler angles over here in the blue font. Okay. Okay, now that we've spent so long learning what a transformation matrix is, here is what where they all live in ROS, a transformation tree. So this tree is TF2's live database of every frame relationship on the robot. So it maintains this live tree, and every arrow here is exactly one homogeneous transform. So this arrow is the transform between map and the ODOM frame. So you don't have to, so on your software, you don't have to calculate this. You just have to give a simple command and the TF2 will output you the values in your required coordinate frame. But there are two types of transforms here. So these arrows are of two types, static and dynamic. Static transforms are ones that never change. Say my camera is fixed on the robot base. I know it's offset from the arm, so that transform exists, but it doesn't really change with time. But a dynamic transfer, for example, between two joints. Now, as the joints move, this changes. Hence, it's called a dynamic transform. Now, another thing we'll have to look at is DH parameters. These are a simple way, systematic convention for placing coordinate frames on robots in a consistent way. So you have four parameters: joint angle, link twist, link offset, and link length. And this is the matrix that uses them. It's similar to the homogeneous matrix, just under a different convention. Now let's understand what each of these means. I will show you all a visualization. Okay. Okay, so first let's look at D. D is the distance along the common joint axis or the old Z axis between the two origin points. So you can see as it moves while I change D. Now what is alpha? Before I do that, 1 second. Okay, so now what is A? A is the distance along the common normal, basically the distance between my two Z axis along the X axis. So this is A, this is also your link length. When you have two revolute joints about the same, that are rotating about the same axis, the link length is what A is. And then we have theta. Now, theta is the rotation of your old x-axis above the z-axis to map itself to the new x-axis. You can see how the x-axis is rotating about the z-axis when I move theta. The final thing is alpha, link twist. Now, this is rotation of the new z-axis about the x-axis. So here alpha would be 180 degrees because it's completely inverted. And you see as that how that moves. So that was about DH parameters. Now we know where our target is, and we just have to figure out how our arm should get there. Any questions so far? Okay, now to figure out how our arm should get there, the next part is kinematics. This is where all the motion happens. Now, kinematics, it's just the relationship between joint angles and your end effector position. This goes in two directions. Now, in our case, we have the targets and we need our arm to get there. But the arm doesn't move through joints and joint actuators. So the motors, the joint actuators, they need angles and not position. How do you give them angles? That's inverse kinematics. Now suppose I have all my joint angles and I want to know the position of the end effector. How do I do that? That's forward kinematics. Both are very essential. But let's do forward first because it's more intuitive and much simpler. So forward kinematics takes inputs of joint angles and outputs you the end effector position. How does this work? You just chain your transforms. So in this formula, each T is a single 4 by 4 homogeneous matrix for one joint. You multiply them all in order and you get your end effector position. Now this always gives you a single solution because it just uses direct matrix multiplication. Now in the case of our 3 degree of freedom planar board, this is the transformation matrix and this is derived from the DH parameters. Like I said, L is your link a length. When you have two revolute joints, the link length is the distance between both their axes along the common normal. And theta is the value that keeps changing because they rotate, your joint angle. So this is the transformation matrix and this is what we're going to use to calculate our end effector position. Say for example, theta 1 is 45, theta 2 is minus 45 and theta 3 is minus 90. I just have to simply compute each of the matrix and then multiply them to get my end effector position. Now I've done that using this matrix and the length values are the same as in our CAD model. So the length of link 1 is 20 centimeter, link 2 is also 20 centimeter, but link 3 is 10 centimeter. So after I've used all those values, I get the end effector position to be 34.14 centimeter and 4.14 centimeter. Now we can easily verify this on our CAD model. So let's do that now. See, I just have to set these angles. It was 45, 45. Now, on the slides, I've written it as minus 45 because these two axes are inverted. This is clockwise and this is anti. And here 90. And you can also check the link lengths. This is 20 centimeter, this is 20 centimeter, and this one's 10. Now, if I want to find the end effector position, you can see the vertex x. It's at 34.14 centimeter and 4.14 centimeter. So our math was correct. Okay, we can also look at this in visually. So this is for forward kinematics. I can select each of my joint angles, and what this says internally is the same thing. It multiplies this kinematic chain, T theta 1, T theta 2, and T theta 3, and then outputs the end effector position. Okay, so first when I move joint 1, you can see that the end effector traces a complete circle. Now this circle is the workspace. It encloses all the possible values of the position values of the end effector for respective theta values of all the three joints. Now, if I move joint 2 and then joint 3, the end effector position changes along with it, and it computes this using the transformation chain. Now let's get back. Now that we've covered forward kinematics, we have to do the inverse. But inverse is harder, and we should look at why. First is that multiple solutions are possible. And the math fails when the target is out of the workspace. And it also gives you singularities. Some configurations cause the math to divide by 0, and that's literally undefined. But there are three approaches to solve inverse kinematics. First is the geometric approach. This is for simple arms, 2-degree or 3-degree planar arms. You use pure geometry and trigonometry, draw triangles, and then do the math. Then we have the analytical approach. You write down your complete transformation equation and solve it algebraically. It can get messy really fast for complex sums. And hence, then we have the iterative method. Now let's get back to our problem of why you get multiple solutions. So say I want to reach this green, that's my end effector position. I can either do elbow up or elbow down. So I have two solutions for a simple planar case. But as it gets more complex, I can get multiple solutions. Now that I have two solutions, both mathematically reach the set position. But which one would you pick and why? If anyone would like to answer. Okay, so in real robots, the solver picks the solution closest to the current joint configuration. So the arm makes the smallest possible movements. If both are equally close, it checks for collision, or if you're near a singularity, it avoids that configuration. Now let's calculate for our end effector position. We know the position to be 20, 20 centimeter. To take a simpler case first, let's assume that link 3 is always parallel to the x-axis. So essentially, this converts it to a 2-degree of freedom problem. And we know that the length of the link 3 is 10 centimeter. So instead, we just have to find angles such that link 1 and link 2 combined reach 10, 20. We're considering that link 3 length along the x-axis 10, so that's why this is 10, 20. Now let's look at this simple triangle. This is theta 1, the angle of joint 1, and theta 2, angle of joint 2. We can calculate theta 2 pretty simple from this yellow triangle, just using the cosine rule. And then theta 1 again using simple geometry. This is from this huge triangle, and then you subtract this angle. And then you get theta 1. Now this works for your 2-degree of freedom case. So now in this case also, it mimics the same thing. The link 3 is always parallel to the x-axis, so it's just basically a 2-degree of freedom arm. And this is the workspace for the entire 3-degree of freedom planar arm. So now if I, in this position, you have two configurations, elbow up and elbow down. Here I've also added a camera mount, so you don't want your arm to collide with it. So I have two solutions and this collides, so I take the orange solution. And say for another point, again you get a collision. Now for these points you get two angles, and like I said before, you choose the better one, which gives you less work. Now if I go further away, I don't have a solution anymore because this is out of the workspace, so the math doesn't really give a solution. Now this circle is for the workspace when you could independently move your link 3 also, but now since I've constrained link 3 to only be along x-axis, the workspace is reduced. So say at this point only you don't get a solution. And if you go further away from the final workspace, you get a warning, target outside the working range boundary. So this just uses simple math to solve it. But there are other methods for when it gets even more complicated. But before we do that, let's look at a 3-degree of freedom planar arm. sorry, a non-planar one. So non-planar 3 degree of freedom. So the first joint would rotate about z-axis while the other two joints rotate about y-axis. Now the math for this, if you want to do it using the analytical method or the geometrical method, is complicated unless you use a trick. So let's look at this from above. So the entire arm, this part of the arm doesn't lie in the x naught z naught plane. It lies in the x1 z naught plane. And x1 is at an angle theta 1 from x naught. So when you look at it from above, this is what you'll see. So you can easily find theta 1. It would just be tan inverse y by xt. Another way to look at it is draw a perpendicular from your end effector position. And then this distance would be your xe and this would be your ye, and you can get theta e from the tan inverse. And doing this just simplifies the rest of it to the previous 2 degree of freedom case. You use your cosine law and simple geometry to get the values. Now that was so much geometry. There should be an easier way to do this. And obviously your solver doesn't use this method. It uses a numerically iterative method. And the key tool here is a Jacobian matrix. What this does is it maps joints velocities and end effector velocities. X dash is equal to j theta theta dash, where j theta is a Jacobian matrix. Now how does this work? The algorithm. It starts with a guess and then it calculates the forward transform. Where does the end effector actually end up? Then it measures the error. How far are we from the target? And then it uses the Jacobian to figure out the next step. And then it takes a small step towards that direction. And this Jacobian is this inverse equation. Delta theta is equal to j inverse delta x. And then you repeat this until the error is small enough. So you have predefined libraries like MoveIt for ROS and IKPY that implement for this for you. So they go over this loop thousands of times and give you the final joint angles. Now let's trace through everything we've done so far. The camera sees pixels at 320/180 and it uses camera calibration to convert it to values in its frame, XCOM and YCOM. Then we apply a transformation using the camera offset -5, 10 to transform the coordinates from the camera base to the arm base. Then we get our final sample value at 20, 20 centimeter. Then we run inverse kinematics on the 3D of arm with the target as 20, 20 centimeter, and then we get our values of theta 1, theta 2, theta 3. And this is sent to each of the joint actuators. And the arm is moved. Then we can also check if it's actually there by using forward kinematics. So this is what we've done so far. We've after coordinate frames, we've done transformations, rotation, translation and rotation, and under rotation we've covered the rotation matrices, the homogeneous transformation matrix, DH parameters, Euler angles, and gimbal lock and quaternions. And under forward and inverse kinematics, methods to solve them. In inverse, you have your iterative Jacobian method. Any questions so far? Okay then, now the last part. We've built our arm in Fusion 360, the joints are set, the materials are assigned, and inertial properties are also computed. But now what? How does this robot become a robot that you can run on your simulation software? The answer is URDF, Unified Robot Description Format. It's an XML file that describes everything about your bot, every link, every joint, all in a text format. And all the simulation softwares, Gazebo, ROS2, they all speak URDF. It's basically the golden standard for ROS. Now, when you export your Fusion 360 model to get to a URDF, you get a file that contains the visual mesh and the collision geometry. Now, visual is what it has your detailed textures and geometry. This is exactly what you model. This is what you will see rendered in your final simulation. So it includes all the aesthetic components. Now the collision geometry is a simplified version of it. Instead of all these components, you just use simple rectangular cuboids and cylinders. So why do we do this? To make the physics calculation easier. So it has the exact same inertial properties as your visual model, just in a cleaner model, just in a cleaner shape. So it is optimized for fast physical simulations. Now this is what a URDF export would look like. The key tags that we should note is first a link. This defines a rigid body, one component from Fusion 360. So again, remembering that all your links should be different components whenever you have to export it. Next, we have a visual tag. This is the STL mesh file. This is your Fusion 360 geometry that is exported. Then we have a collision tag. This is the simplified cylinder or box, and you don't have to do anything. Fusion to URDF generates this automatically based on the bounding value. And then we have the inertial tag. This is what contains your inertial information: mass, moment of inertia, and center of mass. And this comes directly from your properties in Fusion 360. And this is why assigning the right material matters. Then we have a joint tag. You can see over here the origin and the x-axis. So this is rotation about the z-axis, and also limits. So the limits that you have set in your model appear here. So every single thing that we've learned today is all in this file, and it all connects. Any questions? Okay, then thank you. If anyone still has any questions, you can ask.
Guys, you can raise your hands and we'll unmute you so that you can ask your doubts.
Hello.
Yes.
Which software do you guys use to visualize 2D planar and to solve inverse kinematic equations?
That was a Pygame script.
Which one?
Pygame. A Python Pygame.
Okay, okay. Thank you, ma'am.
Any other questions, anyone?